Today we're going to talk about fine-tuning LLMs and how do we make LLMs reliable in production environments. So the agenda for today, we're going to discuss about the problem of reliability in LLMs and why is it a hard problem to solve, and when should you consider fine-tuning LLMs to mitigate this issue, and how does fine-tuning work? So we're going to talk about how fine-tuning works, real-world use cases, application of fine-tuning, and common pitfalls and best practices when you fine-tune LLMs that we have seen across multiple customers. So if you probably have seen some of these headlines recently about AI chatbots going a little bit wild. In this case, there are multiple instances where it's hallucinating information, like in the case of Air Canada, it gives false information about the price of the ticket, which actually results in lawsuit. In another case, the AI model is recommending to drink like a bleach and anti-poison sandwiches, which is complete nonsense, obviously. And in a more serious case, the chatbot actually recommended or encouraged a teenager to commit suicide, which unfortunately the person did. So this also resulted in a lawsuit against the company. So you might ask why the LLMs are so misaligned compared to misaligned to what we wanted to do. So this actually goes back to the architecture of the LLM itself. We have to remember LLMs are probabilistic machines. What we call hallucination is actually baked into the system. Pretty much what they do is basically they try to predict the next token given an input sequence of token. They try to predict what is the next likely token to tell. And this prediction is basically not grounded on any information. So it's only trying to predict based on an input, based on this training data that was trained on. There's no factual information. There's no ground truth data that's it's based on. So basically it makes it really not controllable and makes it very sensitive to the input sequence. So if you change the input slightly, you will get like a different output because it's just a word generator. It's trying to generate words based on an input sequence. So this is actually what we call hallucination, is actually a feature in this LLM where it's baked into the system itself. So how do we actually make them more reliable given this very big limitation in them, right? Like you can't really make them more consistent this way. So there are different ways. The most common way is prompt engineering. So in this case, you basically craft different prompts and try to kind of guide the LLM based on that prompt. This is a good example of a prompt that was actually developed by Apple Intelligence, and they were trying to basically reduce hallucination in the LLMs. And the prompt was as simple as do not hallucinate, do not make up factual information. Obviously, if anybody worked with LLM know that this will not work. Because you're not actually solving the problem. You're just adding the input token to the LLM and trying to guide it. You're not changing the underlying model. So this is actually what makes LLM really not reliable. This technique is actually not reliable, and you really have a limited control over the model behavior. The next way of reducing this hallucination is retrieval augmented generation. So this is basically feeding the LLM with a ground truth data, like your own business document, and then when the LLM generates the output, it's going to generate based on the data that you provided it. So it's more grounded on your own business documents. The only disadvantage that we see here is the infrastructure can be a little bit complex, so you need to rely on vector databases, and also the retrieval process where it tries to find the relevant documents to provide to the LLM are usually kind of not super reliable and can be brittle in some cases. So the next level or the next method is basically to fine-tune these models. So here we're actually changing the underlying mechanism of the model. So we're changing the weights of the model. And the advantage here is you get really highly accurate responses for that specific task that you trained it on. And you can make the LLM learn and understand your domain knowledge. The only advantage here is that we see is this process is a little bit complex and requires training data. So the training data is really hard to get, and we'll discuss later different techniques. But this is also one of the big disadvantages of this technique is it requires a lot of upfront investment to get it right. So when should you really fine tune? So can we just like jump on fine tuning as soon as we have like a specific task we want to accomplish? So that really depends on two factors. So the accuracy requirement. For example, if your accuracy requirement for your task is pretty low, doesn't require high accuracy, prompt engineering is probably enough. So this is, for example, generating an email, generating like a poem or generating like a food recipe or whatever. The accuracy requirement is really not that high. Prompt engineering is probably good enough. Now, on the other hand, if your task require accurate answers based on external documents or external knowledge, like, for example, legal assistant, then in this case, you want to do retrieval augmented generation with some prompt engineering. And the next phase where you need fine-tuning is where you really need to have you want to be in the high accuracy regime. So this is, for example, information extraction from financial document and sensitive documents, fine-tuning the model to follow your own tone, generate the content like that will follow your own brand style. This is where you need fine-tuning. And the final quadrant is hybrid. So this is, for example, where you need like a customer, you deploy a customer support agent, and you want the customer support to not only reply in your own brand and tone, but also use external knowledge based on your business. So we're talking about like customer support agent, legal agent, and so on. So this is where you really need fine-tuning. Otherwise, these techniques are probably good enough. So the best strategy that we recommend is usually start with prompt engineering first. So you start with off-the-shelf LLMs and do some prompt engineering, measure the accuracy of that specific task. Let's say if it's summarization or classification. So start with prompt engineering first, and then try to measure. If that doesn't work, if that doesn't meet your accuracy requirement, we recommend to go to the next level, which is going to fine-tuning. And this requires typically at least 100 examples. You can give it the more example, the better, but 100 to 5,000 are usually required for this process to go. And then if this doesn't work, like if fine-tuning is still not good enough, then you have to do like continuous pre-training, which it's a more involved process, and it's actually out of reach for most companies. And then obviously training from scratch the LLM, which is absolutely not possible for most startups. So this is for like bigger company like OpenAI and so on. So realistically speaking, we're talking about like 1, 2, and 3. So these are the sequences that we usually see clients do. So in this talk, we're going to talk about fine-tuning. So we will explain what do we mean by fine-tuning. So fine-tuning are before I explain fine-tuning, actually, I want to show here like a study that was done by one of our friends at Predibase, and they basically benchmarked different models. These are open source smaller models on multiple tasks like reasoning, math, and coding, and so on, and they show the effect of fine-tuning compared to non-fine-tuning. And here, what you can see here is after fine-tuning, this Llama 3 8 billion parameters is able to get like 75% accuracy across all the tasks. And then you can see basically without fine-tuning, it's much, much lower than that. So fine-tuning actually does work, where it boosts the performance even more. And the most interesting thing here is if you go down this leaderboard, you see GPT-4, which is basically the closed model. It's actually at 66% accuracy across all these tasks. What this means is like basically the fine-tuned smaller LLMs, 8 billion parameters, are beating the bigger models when they are fine-tuned on those specific tasks. So we're talking about like a trillion parameter model compared to like a few billion parameter models. So fine-tuning does really work here. And here they show basically the different the ratio between GPT-4 performance compared to fine-tuned models. And you can see here for most of the fine-tuned models, they're actually beating GPT-4 on reasoning tasks, knowledge tasks, natural language processing tasks, and math. The only task that fine-tuned models are lacking, like training behind, is in coding. So coding is still, the bigger model, foundational model, is still like beating fine-tuned models. But this basically shows that fine-tuning has tremendous benefits across multiple parameters. First of all, you can basically guarantee that you can get really high accuracy on your specific task, like we said, for example, like for content generation or information extraction. On the other hand, for the base model, you don't know, so you do prompt engineering and you iterate on that, but there's no guarantee really you will reach that level of accuracy that you need. Second, the inference speed. So with smaller models that are fine-tuned, you can actually decrease the latency significantly compared to the closed source model, the bigger one, where you have no control virtually, basically. The cost will be also extremely cheap compared to the base model, the foundational closed source models. Privacy and security, obviously, these fine-tuned LLMs can be hosted on your own private network or your computer, and your data will never leave your environment, so you're completely secure in that, as opposed to the closed source where you have to send your data out. Now, the disadvantage of this is the complexity. So these fine-tuned LLMs, to fine-tune an LLM is actually a pretty complex process, and we'll see why is it complex. And also, it requires training data. So this is another limitation, where the training data is pretty hard to get, and especially high-quality training data, it's kind of pretty tricky to do. So these are overall, we see like a tremendous benefits with fine-tuning LLMs compared to base models. Now, how does fine-tuning work? So there are actually two processes. The first one is what we call supervised fine-tuning, and the second one is reinforcement fine-tuning. So supervised fine-tuning is basically, giving the model a data set and trying to ask it to learn from that data set. So if you take an analogy of a student, it's like you're giving a student like a math book or geology book, and you are asking the student to read each page and learn everything from that book. Becomes very proficient at that task. Reinforcement fine-tuning is you want to basically align the model on a human preference. So going back to the analogy, so you want to teach the student specific strategy how to solve a math problem. So there's a preference. So it's not any strategy you want it will work. You basically want it to follow a specific strategy. You want to align it better. So typically we start with supervised fine-tuning, and then we go to the reinforcement fine-tuning after that. So the standard in supervised fine-tuning nowadays is called LoRA, so low-rank adaptation. And this technique actually unlocked a lot of potential for companies to fine-tune their own LLMs. So the idea is instead of fine-tuning all the weights and all the parameters of the model, we're talking like billions of parameters, so you actually freeze the majority of the weights of the base model, and you only fine-tune a small subset of the model. So it's two small matrices, A and B. And then what you do is you merge this fine-tuned subset that was fine-tuned on your task with the frozen weights, and then you end up with a merged model that has the knowledge of the base model plus the fine-tuned adapters or the weights on your specific task. So like email generation, content generation, whatever. So you basically can combine the generic knowledge with the fine-tuned adapters. So this will make it basically you'll be able to get almost the same performance as full fine-tuning with almost 10,000 time reduction of parameters to fine-tune. So it requires much less resources. It's way cheaper than fine-tuning entire models. So there's a really like breakthrough that unlocked a lot of things. So reinforcement learning, on the other hand, is slightly different. So instead of providing a data, like a labeled data set, you basically prompt an LLM to generate a response. And then after that, you rate the response. So you give it like a reward data. Is this a good response or is this a bad response? And then after that, you collect that reward data, and then you reinforce the model or fine-tune the model on that reward data. So you try to maximize or optimize on that reward function. So this, as I mentioned, it helps to align the LLM on the human preference, but also improves it on selecting the correct reasoning strategy for the task. So what are kind of the common use case that we see in fine-tuning? So where we see companies using fine-tuning? The first one is content generation. So here we're not talking about like any content generation, like email generation. We're talking about like technical content generation. We've seen legal firms, for example, fine-tuning LLMs to generate patent claims. Usually those are pretty technical. They have a lot of legalese, and they need to follow a specific structure. So we've seen actually doing pretty good with that. So fine-tuning LLMs on legal documents. Another one we've seen that's very common is the fine-tuning on content marketing. So basically, fine-tune the LLM to generate like content that follow your own brand and style. There's also product description generation. We've seen like real estate companies, for example, fine-tuning an LLM to generate like a product description or like a description for real estate that will really follow their brand and tone. So practically, how does it look like? So here, just want to give you an example where we fine-tuned an LLM on LinkedIn posts. So here we show, for example, we ask the LLM to generate a LinkedIn post based on actually the topic of this talk, making LLM reliable. So as you can see, before fine-tuning, it follows the regular style. You can tell very quickly this is AI generated. You've probably seen many of these in LinkedIn recently, but this is very, very like common kind of AI generation. Now, after fine-tuning, this is the result of fine-tuning. We can see that the LLM is more personal. So like the current state of LLM is not acceptable. They hallucinate too much. Hallucinations that are problem, not an AI problem. I've been saying this for years. So we basically, what we did is we fine-tuned the LLM on a specific influencer style. And then the generation became much more personal and more aligned with that specific influencer. So this is the kind of the difference that you can see a stark difference between the two here, before fine-tuning and after fine-tuning. Now the next task that we see that's very common in when fine-tuning LLMs is document understanding. So we've seen companies basically fine-tuning AI models and LLMs to do legal clause extraction. This is a very technical task where you need to identify, red flags, confidentiality clauses, and so on. So you have to be very accurate exactly in the boundaries where you can extract that clause. We've seen also using it for information extraction for financial reports. So here, basically, as you know, financial reports are a little bit unstructured. So they have a lot of tables, diagrams, and unstructured text. So if you can fine-tune an LLM to capture specific information from that financial report. The third task that we see in document understanding is PII masking, and here basically fine-tuning an LLM to identify personal identification information from sensitive documents and then masking them accurately. So you want to be in the 95% accuracy and higher. In this case, you probably don't need to fine-tune LLMs, or you can fine-tune smaller models, but you could also fine-tune LLM for more flexibility. So this is an example of legal clause extraction where we can see, I think a little bit hard to see, but the orange here is the score, the F1 score, precision recall after fine-tuning, and the blue is before fine-tuning. So we can see like significant increase after we fine-tune the model on legal clause extraction. So this is another example where you can see like significant increase after fine-tuning. Another trend that we see is fine-tuning for agent use. And here, what we see is people fine-tuning for agent reasoning. So you want to basically the LLM to follow a specific chain of thoughts for solving a specific problem. So you can do like supervised fine-tuning plus reinforcement learning. Another technique we saw is fine-tuning for tool use. So given a user, user input, you want the agent to use the correct tools appropriately. So you can provide the training data, and then you can fine-tune it on that. And finally, reinforcement learning, where you observe, or you basically fine-tune based on the action that the agent take in a specific environment, and then you give it a reward data, so it actually behaves better in that environment. So practically speaking, look, what does it take to fine-tune a model? So there are actually multiple steps. That's why I said it's a little bit of a complex process. The first step is the data preparation. So you need to collect the data. So this is whatever data you have, could be conversational data, transcripts, legal data, whatever you have. Or if you don't have data, there's also a way to create synthetic data. So this is the first part. After that, you need to do labeling. So this is where I mentioned earlier, this depends on the task in hand. So you might have like, reinforcement learning data, classification data. So you need to label the data with your human subject expert. And then you do post-processing. So typically what you do after you label, you have to kind of clean the data or like chunk the data or tokenize it, and then before you start the training. So the second step is the training itself. This is actually the easy part. It's really not that hard nowadays. So you start with selecting a base model, like a Llama model or a Qwen model or a DeepSeek model, and then you load the data that you labeled and you cleaned. And then you train the model using supervised fine-tuning, like we mentioned, or reinforcement learning, and then you finish the training. So after that, you basically run prediction on the validation set. So after the model is trained, you want to basically run prediction on a test set, and then evaluate the model on that prediction, on that test set. So there's the different metrics you can use, like an F1 score, precision, recall, rouge, bleu. Depending on the task, we'll talk about it later. There are different metrics that you can use. And finally, you can deploy the model if it meets your accuracy requirement. You can deploy it in production. But here it's not done yet. So basically, after you deploy in production, typically what I've seen people do is basically keep monitoring the model in production and then feeding the data back to the training loop. So this is as you run in production, you keep collecting data, you can relabel the data, and then continuously improve the model over time. So it gets better over time. Why do we really, let me go back quickly here and just focus on labeling. So why do you really need to label the data? So labeling actually has two different benefits. The first benefit, obviously, is the labeled data will adapt the model on that specific task. So if you label data on summarization, you're going to fine-tune on summarization or classification or generation or whatever the task you care about. So the labeling helps to, that's the training data that will fuel the model. But we've seen also recently companies labeling the data to evaluate base models. So before they even start fine-tuning the model, they will label the data. This is the ground truth, to basically evaluate different LLMs. So they benchmark different LLMs based on their own internal labeled data. So it serves two purposes. First is for benchmarking, but also for fine-tuning later. So it's very important to label the data correctly and have really high quality data. So there are different types of labeling. There is as I mentioned earlier, information extraction labeling. So here, basically, you label entities in different documents. You label classes, you label relationships in the documents, and the goal is you want to train a model to capture this information, to extract that information. The second type of labeling is instruction tuning or instruction labeling. So here you provide a system prompt, a user prompt, and the desired response from the model, and then you feed that to the model to basically get trained on. And finally, reward labeling. So this is reinforcement learning by human feedback. So basically, as I mentioned, you look at the output of the LLM, and then you rank the data or you rate the data. So there are three different types of labeling that we've seen at least in the text, in the realm of text. So after the training is done, as I mentioned earlier, you need to evaluate the model. And here, it's very important to get this right, because this will define how would you it will define kind of the threshold that you would consider as good to go, basically. So evaluation basically serves multiple purposes and can be used depending on the domain. So, for example, if your domain is training a customer service chatbot, you might care about problem resolution. So you want to evaluate the model on how the percentage of problems being resolved, maybe politeness or clarity or brand voice. Let's say your domain is research analysis. You want to have a metric that will reflect, the depth of the insight that the LLM is providing, the relevance, actionability. So if your task is information extraction, like we mentioned earlier, like legal clause extraction, you might care about accuracy, false positive, precision, recall, confusion. So there are actually multiple dimensions that you can use to evaluate your model. So here this is a small list of different evaluation that are typically used for classification tasks. By classification, I mean like entity extraction or text classification. There's the blue score, perplexity, rouge, meteor, F1 score, Levenstein distance. This is just a few lists, but these are all different metrics that you can use to basically evaluate your model. For text completion, this is text generation or like reasoning tasks. You can evaluate with a human feedback. So you have like a real human rating the data. Or you can, what I've seen being used is using like an LLM as a judge. So basically using another LLM that you prompt. So in this case, we prompted an LLM to give us, a rating for hallucination. So you can basically prompt an LLM to evaluate a specific dimension or metric. Obviously, here you're relying on prompt engineering, which is not great, but still better than nothing, better than with no evaluation. And then you have also the fine-tune. You can fine-tune LLM to evaluate another LLM. So this is, there are different ways of doing this. You can fine-tune a specific data set, evaluation data set, and then you can use that LLM to evaluate another LLM. So the common kind of pitfalls and best practices that we've seen. The first one is overfitting. So when you are dealing with, when you're trying to fine-tune a model, one of the main issues that we've seen is overfitting. So if you provide with unrepresentative training data, that means a little bit biased. It's not like, it doesn't have good distribution compared to your production data. You will probably end up in overfitting and the model will have low performance in production. Low quality data is another problem where you can have, you might have inconsistent quality, inconsistent like training examples quality, and this can lead to poor model generalization. Bias is another problem. As I mentioned, it's very similar to related to overfitting, where the distribution of the data doesn't follow the production distribution. This is another problem. And we've seen people not doing monitoring. This is also another problem, where you can, where people just like, publish the model in production and without any evaluation, and they will end up with like the model performance drifting and degradation over time. So the best practice is basically the first thing you need to set up evals and rules before you even fine tune. Like I mentioned earlier, if you can label some data, some ground truth data, so you can evaluate your models, that will be the best case scenario before you even get started with fine tuning. Definitely involve subject matter expert in your field. Quality is definitely more important than quantity in this case. So definitely have like subject matter expert, like your lawyer or medical, expert, whatever your task is, to be involved in the data preparation. And also definitely continuous monitoring. Make sure that you set up your evals from the beginning, and as your model is running in production, each interaction with the model is being logged, so you can actually track, the progression of the model over time and if it's degrading or not. So these are the three I see like best practices that should be implemented. If you're, to be honest, for any like LLM project, these needs to be kind of implemented. So basically, we at UbiAI, what we did is our mission is to basically streamline this entire process. So we want to make it, we understand it's a little bit complex, so we want to make it like more streamlined. So we created this application where you can basically, label your data, you can fine tune your model, and have that feedback loop of evaluation that's happening all in one platform. So you don't have to jump from one platform to another for fine tuning or evaluation or deployment. So everything is kind of contained with one platform, and you can see real-time metrics as your model is being deployed. Yeah, if you're definitely curious about UbiAI, please reach out to me. And thank you so much for your attention. So this actually concludes the talk. If you would like to connect, please join our Discord channel using this QR code. You can connect with me directly on LinkedIn, and we'll be very happy to discuss. Thank you very much.
Thank you. I think if people want to stay, we can have extend a little bit more so that we can cover the questions. And for folks who have other plans, feel free to move on. Thank you. So one of the questions that was raised is, if I have a lot of custom data, technical documents, including commands, command versions, code snippets, and I'm talking about the range of roughly about 10,000 plus documents, which needs to be used in an internal chatbot. What base model would you recommend to fine tune? How would you deploy this model at scale?
Yeah, I mean, as I mentioned earlier, so I think you have to do a benchmark exercise. So first of all, you prepare the data, and then you basically evaluate each single model on that specific data. So you cannot really tell from the beginning like what model is the best for what task. You basically have to do it based on data-driven, basically, decision. So that's why I'm saying the label data set is so important, because this will define your benchmarks. You cannot just use a generic data from Hugging Face or whatever. You need to basically create your own business data, labeled business data, to be able to evaluate these models for that specific task. And the second question, I think, Mario, was like, how do you deploy in production?
Yeah. How do you deploy it? That's good.
Yeah, I mean, it's actually pretty simple to deploy it, thanks to this LoRa technique. So basically, once you fine-tune it, you have these adapters, and then you merge the adapter with the base model, and then you can basically fine-tune it. Deploy it in like cloud provider. You can deploy in our platform as well. There's also Hugging Face deployment. There's like multiple providers there. But the key is really the data, I think.
Next question. Can we fine-tune models not hallucinate with RAG? I know that if the data I need is not in the vector database, it can say, I don't know. Mm-hmm. With FP models alone, meaning no RAG, would it hallucinate or make up answers if it is not trained on the prompt it receives? If so, how do you prevent this?
Yeah, that's a good question. Yeah, I mean, I think RAG, I think it's hard to tell, to be honest. I think there's still going to be hallucination even with fine-tuning on your own like data set. That's why I'm thinking, if you combine RAG with fine-tuning, you get actually the best of both worlds, where you can mitigate based on like RAG, using RAG, but also, when you fine-tune it, you basically make it more closer to the truth of that data set and make it even more robust, I think. So, but I don't think you can remove hallucination 100%, even with fine-tuning.
Next question. How much data needs to be manually assessed for effective reinforcement learning?
Yeah, that really depends on the task. We've seen people claiming like even 10 examples are enough for reinforcement fine-tuning. From my experience, anything less than 1,000 is not going to give you a good performance. So typically, if you have like 1,000 examples that's already ranked, that would be the best case scenario. I really don't believe with 10 examples are enough. Definitely, you need. From my experience, from what I've seen, like at least 1,000.
The other question is, writing style may be achievable using few shots prompting.
Yes.
So what kind of use cases benefit from fine-tuning than few shots prompting?
That's a good
What is your recommendation on fine-tuning small models versus knowledge distillation? I think we can break it down into two. First question, what kind of use cases benefit more from fine-tuning than few shots prompting?
Yeah, that's a good question. You could do it. You could basically improve the content generation with, in context learning and many shots. But there are like kind of few drawbacks of that. First of all is the context window. So you need to feed a lot of data, a lot of examples to be able to capture the nuances of that content or that style, which makes it basically increase the latency and makes it more expensive. With fine-tuning, you don't even have to do that. So you just like fine-tune it once with a smaller model, and you don't have to add any examples, just like it will work out of the box with fine-tuning. In terms of the quality, I think with fine-tuning is more guaranteed, but with in-context learning and many shots, you have less control over this style, I would say. So I think fine-tuning is usually more robust, but I definitely don't. I'm not discounting many shots. I think that's also a good way to do it. It's just a little bit more expensive. You have a little bit less control. So fine-tuning helps in terms of these two.
Follow-up question. What is your recommendation on fine-tuning small models versus knowledge distillation using small models?
I mean, knowledge distillation is essentially kind of very similar technique. So knowledge distillation is basically you prompt an LLM and then you extract that information from an LLM. That you get the output for that specific prompt. You create multiple prompts and get multiple outputs, and then you collect that data set, and then you basically use it to fine-tune a model with it. So I think knowledge distillation is actually a technique to help fine-tuning for sure. So yeah, they work hand in hand for sure.
Okay, thank you. Next question. When is it worth fine-tuning the best possible model over a mini version of that model?
What is the best way to say it again? Sorry.
When is it worth fine-tuning the best possible model over a mini version of the model? I think the ask is more like, I have two models. There's the regular model, then there's the mini. And the idea is, when is it worth tuning that model versus the smaller model? This might be related to the talk that you mentioned, that the smaller model has proven to be more accurate in some cases.
Yeah. I mean, you could. I'm not. So if I understand the question correctly, when is it better to fine tune a smaller model compared to fine tuning a bigger model? I'm not sure if that's the understanding, but like fine tuning a smaller model, from my point of view, is always the go-to solution, if possible. Whenever I care about accuracy and relevancy, I usually try to basically fine-tune a smaller model as opposed to using the generic one for many reasons, right? Like as I mentioned earlier, you have more control over the accuracy, the speed, the cost, the privacy. Even if it's a mini model, that probably might give you kind of almost the same accuracy. I usually prefer the fine-tuned smaller model versus the mini models for these reasons here. Yeah.
Last question. What can we do if continuity is lost in the documents that are page by page, and when trying to search for the document, nothing is returned or the agent hallucinates? So I think the question is more hallucination. What can we do if the continuity is lost in the documents that are, I'm assuming, let's say, an agent is parsing a document page by page, and some sort of continuity is lost, or there's some hallucination, and maybe the ask is more related to, what are the things that you can do?
Continuity is lost. Okay, so that means like you have like long documents and it doesn't fit in the context of the model.
Yeah, most probably. Let's say maybe a contract that's like 200 pages,
right,
to consume, and basically,
yeah. With fine-tuning, you don't like feed the entire 200 documents to the model. You chunk it in smaller sizes because the model has like a specific context length. So the first step is you chunk those long documents, and then yeah. So in terms of continuity, so in the inference side of things, I definitely probably recommend to include some chunks. Like if the continuity is very important, include some chunks in the prompt of the model, in the context of the model, and then when you're running inference. So basically just like include maybe the 3 chunks before or after, and then so you can add more context to the model when it provides response.